settle in and let your breathing slow down a little, like you have nowhere else to be. The room can stay dim, the world can stay outside, and nothing in the next few minutes needs to be solved. Tonight, we are going to talk about time dilation, the quiet fact that time does not march the same way everywhere. Not in a dramatic, movie-ready way, more like a soft drift where two honest clocks can disagree and still both be correct. With the Sleepless Scientist keeping things gentle, we will wander through seconds, atoms, speed, and gravity, and notice calmly how now can stretch without breaking. Here is the soft problem of now. It feels universal, but it is not managed by a single office. There is no cosmic timekeeper, no supervisor with a clipboard, making sure every second is stamped and approved. There is only the universe doing what it does and letting each place keep time in its own slightly biased way. You already know a human version of this. Some minutes feel like wet cement. Others vanish like a soap bubble in warm air. That is psychology and caffeine and dread. But nature has a quieter version that does not care about mood. Two clocks can run at different rates, not because one is broken, but because they are living under different conditions. The good news is that the effect is usually so small that your life survives it just fine. The bad news is that the universe does not care about your convenience. It never did. It just happens to be polite enough to hide the weirdness behind tiny numbers. Until you built satellites, particle accelerators, and clocks that refuse to lie. So, we will take this gently. No frantic equations, no heroic music, just a calm tour through what a second really is, how we decided to define it, and why motion and gravity quietly bully it into stretching. And once you are comfortable with the idea that time can be a little flexible, we can start with the simplest question: what a second even is. A second sounds like a hard thing, like a brick, like you could hold it, label it, stack it with other seconds into a wall. But a second is not a substance. It is an agreement, a shared habit, a human choice about what rhythm we will count. For most of history, a second was whatever the sky was willing to give you. You looked up, you watched the sun drag its light across the ground, and you carved the day into pieces. Sundials were honest, but they were also moody. Clouds could erase them, winter could tilt them, and the earth itself, inconveniently, does not rotate with perfect steadiness forever. So we invented better rhythms. Mechanical clocks were a beautiful compromise between physics and stubbornness. A swinging pendulum, back and forth, like a metronome with a mild headache. A balance wheel, vibrating in a pocket watch, trying its best while being jostled by walking, temperature, and the general chaos of having a human attached to it. A pendulum clock is soothing, but it is also vulnerable. Heat makes parts expand. Cold makes them shrink. The lubricant thickens. The metal flexes. You might not notice in a day, but the clock notices. It drifts. Every mechanism drifts. Eventually, because matter is not perfectly rigid, and friction always wants its cut. Then, we got more ambitious. We learned that if you want a steady beat, you should stop asking gears and springs. You should ask atoms. Atoms have their own internal rhythms, not in a poetic way, in a brutally consistent way. Electrons in an atom can jump between energy levels, and when they do, they absorb or emit light with a specific frequency. That frequency is not a suggestion. It is not a vibe. It is one of the most dependable events in nature. So modern timekeeping, the kind that runs navigation systems and keeps financial networks from tripping over themselves, is built on atomic clocks. The most famous are based on cesium atoms. A cesium atom has a particular transition, a tiny flip in energy state that happens with an extremely regular frequency. We define the second using that. 1 second is a certain number of oscillations of radiation associated with that cesium transition. Not roughly, not approximately, an exact count. This is comforting in a strange way. Time becomes counting. It becomes breath-like in principle. You do not need to understand the atom deeply to understand the idea. A second is the act of counting a regular heartbeat. Only the heartbeat belongs to cesium, and it is much less emotionally complicated than you are. But here is the quietly unsettling part. Even atomic clocks are not immune to the universe. They are steady, but they are not outside reality. They are physical objects, sitting somewhere, moving somehow, bathing in some gravitational field. And those conditions change what it means for them to tick. This is where time dilation slips in, not as a mystical fog, but as a consequence of how the universe keeps its books. Imagine 2 identical atomic clocks, same model, same calibration, same obsessive engineering. You set them side by side, watch them agree, and feel a little smug about your control over the cosmos. Then you separate them. One stays with you. The other goes on a trip. Maybe it rides in an airplane. Maybe it climbs a mountain. Maybe it sits in a satellite, looping around Earth with perfect, indifferent patience. After a while, you bring them back together and you compare. You expect them to match. Why would they not? They are built to be faithful, and they are faithful. That is the problem. They do not match. Not because one failed, but because each clock experienced a different path through the universe, different speed, different gravity, different geometry of time itself. They both did their job. The universe just assigned them slightly different wages for the same shift. This is the heart of time dilation. It is not a glitch in the clock. It is the clock doing exactly what it must do, while the universe changes the rules of ticking depending on motion and gravity. The easiest way to stay calm here is to drop the idea of one master time. Think instead of each clock carrying its own little pocket of now, a private metronome that stays consistent locally. You do not feel time slowed down around you because you are made of the same physics as your clock. If you are in the moving airplane, your body chemistry, your neurons, your sense of boredom all keep pace with the clock beside you. Everything inside your frame is coherent. Your thoughts do not smear. Your heartbeat does not become a slow drum in a distant room. You just live. Time dilation shows itself when you compare across different journeys. The good news is that at human speeds, the mismatch is small. Your life is not torn apart by it. The bad news is that small is not zero. And when you need precision, like with satellite navigation, small becomes important. To see why motion matters, let us take the calmest possible ride, one where the only drama is the speedometer. Picture yourself on a train at night. The kind of ride where the windows are black mirrors, showing you your own tired face, floating over darkness. The motion is smooth, no rattling heroics, just a steady forward glide. Inside the train, everything feels normal. Your coffee cools at the usual rate. Your eyelids get heavy at the usual rate. Your internal sense of time does what it always does, which is occasionally lie, but lie consistently. Outside, someone stands still on the platform, watching the train slide away. If they could see your clock and theirs with perfect precision, they would say something strange. They would say your clock is ticking a little slower than theirs. Not by a dramatic amount, not by a second per minute, more like a tiny fraction that you would not notice without an atomic clock, and a personality that enjoys suffering. But the principle is there. Relative motion changes the rate of time. This comes from special relativity, which is a phrase that sounds like a designer perfume, but is actually one of the most unforgiving descriptions of reality we have. The core idea is that the speed of light is the same for everyone, no matter how they move. That sounds innocent. It sounds like a trivia fact you can ignore, but it is a tyrant. If the speed of light is constant, then something else has to give when you move. The universe balances the budget. Space and time have to adjust so that light never breaks its speed limit. Think of it like this. The universe does not allow you to cheat. You cannot move in a way that makes light look slower or faster. So when you move, your measurements of distance and time subtly reshape themselves so the light rule stays true. From your perspective on the train, you are at rest and the world moves. From the platform perspective, you are moving and the platform is at rest. Both are allowed. Both are valid. The universe does not pick favorites, but they cannot both keep the same definition of simultaneous moments and identical ticking rates. Not if light stays constant. So time stretches gently in the moving frame compared to the stationary one. There is a classic way to picture this that does not require equations. Imagine a clock that measures time using light, a light clock. It is a very simple fantasy device. Two mirrors face each other. A pulse of light bounces up and down between them. Each bounce is a tick. If the clock is sitting still relative to you, the light goes straight up and down. The distance is simple. Tick, tick, tick. Now put the light clock on the train and watch it from the platform as it moves past. The light still bounces between the mirrors, but the whole clock is moving sideways. So the light does not trace a straight up and down path from your platform view. It traces a diagonal, like a slow zigzag. Diagonal paths are longer than straight ones. So from the platform view, the light has to travel farther between ticks. But light cannot travel faster. To compensate, it is stuck at its speed limit. So, if the distance per tick is longer, the time per tick must be longer too. That is time dilation. It falls out like a receipt. No drama required. Inside the train, you do not see the diagonal. You see the light go straight up and down because in your frame, the clock is not sliding sideways. Your ticks feel normal. Your body feels normal. Your entire world is built from the same slowed time, so there is nothing internal to compare it to. The weirdness only appears when two people reunite and compare notes, or when you build a system like satellite navigation that must coordinate clocks in motion with clocks on the ground. At everyday speeds, the dilation is tiny. A commercial airplane is fast, but compared to the speed of light, it is like watching a snail race across an empty parking lot. The effect exists, but it is small, and still it is real. There have been experiments where atomic clocks were flown around the world and returned, and they came back slightly out of sync with the ones that stayed home. You can feel however you want about that. The atoms do not care. The good news is that you have been time dilated your whole life. Every time you move relative to someone else, you trade tiny amounts of time. The bad news is that the trade is not optional, and motion is only one lever. The universe has another, even calmer tool: gravity, the slow hand on the clock. Gravity is often described like a force, like an invisible hand pulling you down. That description works for daily life, where you mostly care about not falling off ladders. But in general relativity, gravity is more like a shape, a geometry. Mass and energy curve space-time, and that curvature tells matter how to move. This is where time becomes something like terrain. Not metaphorically. In the mathematics, time and space are blended into space-time, and massive objects distort it, like a heavy ball on a stretched fabric, except the fabric is not a thing in space. It is space and time itself. When space-time is curved, the rate at which time passes depends on where you are in that curvature. Clocks tick slower deeper in a gravitational well, and faster higher up. This is not because gravity reaches into the clock and fiddles with the gears. It is because the structure of space-time makes the paths through time different at different gravitational potentials. The clock is innocent. It is only telling the truth about where it is. So here is a gentle image: sea level and mountaintops. You stand at sea level with a clock. Someone else stands on a mountain with an identical clock. Both clocks tick. Both people live their lives complaining about weather, checking their messages, trying to remember why they walked into the kitchen. But the mountain clock ticks a little faster than the sea level clock. Higher up, gravity is slightly weaker. The gravitational well is slightly shallower, and time flows slightly more quickly. This is not a feeling. You do not notice it. You do not walk uphill and feel time loosen. Your brain is not a gravity meter in that way, but the clocks notice, and the universe quietly records the difference. It is small but measurable. If you had a very precise clock, you could see differences over height changes that are not even dramatic. The world is full of tiny time gradients, like an invisible slope. This is one of those facts that is both comforting and irritating. Comforting because it means the universe is consistent, even in its weirdness. Irritating because it means the idea of one single global time is not just wrong. It is lazy. If you live your whole life at a higher altitude, you will age, in a technical sense, slightly more than someone who lived at sea level. Not enough to matter for birthdays, enough to matter for physics, and its scales. Near a very massive object, the effect is stronger. Time slows more. Near something extremely dense, like a neutron star, it slows dramatically compared to far away. The good news is that the rule is gentle and continuous. No sudden snapping, no magical boundary where time breaks. The bad news is that gravity does not negotiate. it pulls time along with everything else. Now, because we live on a planet with satellites above us, this quiet gravity effect becomes surprisingly practical. You carry time dilation in your pocket, and you probably use it when you are hungry at midnight and searching for something open. Global Positioning System satellites, or GPS, rely on very precise timing. They work by broadcasting time signals from satellites, and your receiver measures how long the signals take to reach you. From that, it calculates distance. From multiple satellites, it triangulates your position. It sounds simple, but it is built on a fragile idea. If your time measurements are off by even a small amount, your position estimate becomes wrong. Light travels fast, so even a tiny timing error becomes a big distance error. So, the satellites need extremely accurate clocks, and they need those clocks to stay in sync with clocks on Earth, or at least to be corrected in a predictable way. But the satellites are in motion, and they are higher up in Earth's gravitational field. So two time dilation effects hit them at once. First, special relativity. The satellites move quickly relative to an observer on Earth. That motion makes their clocks run slower from the ground perspective. Second, general relativity. The satellites are farther from Earth's mass in weaker gravity. That makes their clocks run faster from the ground perspective. These effects do not cancel perfectly. One wins. The net effect is that satellite clocks, if left alone, would drift relative to Earth clocks. Over time, that drift would break GPS accuracy. Your phone would confidently tell you that you are in a river, or inside a closed bakery, or gently off the side of a highway. Reality would become a suggestion. So engineers correct for it. They pre-adjust the satellite clocks and keep updating them, accounting for the expected dilation. It is one of the more soothing examples of relativity being not just true, but useful. There is something almost cozy about that. The universe bends time, and instead of panicking, we build a system that respects the bend. Then we use it to find a late-night pharmacy, or a friend's apartment, or the nearest place that sells something fried. The good news is that time dilation is not just a theoretical monster under the bed, it is part of the infrastructure. The bad news is that this means it is real enough to be engineered around, which is an unsettling kind of validation. Now that we have seen time dilation doing useful work, we can zoom out and imagine bigger places where the effect stops being tiny. At human speeds and Earth gravity, time dilation is a whisper. But the equations do not change their minds when you leave the neighborhood. They scale up without emotion. Let us start with speed, because speed is the more intuitive lever. You already know what it is to move fast, even if your version of fast is a highway at night, headlights smearing into white lines. As you approach a significant fraction of the speed of light, time dilation becomes noticeable. Not in the sense that you feel slowed, but in the sense that when you come back and compare clocks, the difference is no longer a rounding error. This is where the old thought experiment shows up. The twin story. One twin stays on Earth. The other travels in a fast ship, turns around, comes back. The traveling twin has experienced less time. They are younger, technically, than the one who stayed. People argue about this story because it sounds like a paradox, and humans love arguing more than they love sleeping. But there is no paradox once you track the full journey. The traveling twin changes frames when turning around, and the situation is not symmetrical. Still, the core lesson is gentle. Different paths through space-time can contain different amounts of proper time, the time experienced by the traveler along that path. You can think of proper time as the time your body actually lives through, the time your cells divide and your hair grows and your neurons burn their glucose. That time is what your clock measures when it sits next to you. It is personal, local, stubborn, and it depends on the path. Now, a calm note. This does not mean you can cheat aging easily. Getting close to light speed is not a weekend project. The energy required is obscene. As you push mass toward light speed, its momentum grows and it becomes harder and harder to accelerate. The universe charges you more and more energy for smaller and smaller gains in speed. The good news is that the rules are consistent. The bad news is that the rules are corporate-mandated physics, and the corporation is the universe, and it does not offer discounts. So time dilation is real, and it becomes extreme at extreme speeds, but it does not give you a free lunch. It gives you a different bill. Gravity can also become extreme. Near very dense objects, time slows down sharply compared to far away. You have probably heard of black holes and time slowing near them. That part is true, but it is often described in a way that makes it sound like a special effect. It is simpler than that. A black hole is an object with so much mass packed into such a small region that the curvature of space-time becomes so steep that not even light can escape from within a certain boundary, called the event horizon. Near that boundary, the gravitational time dilation becomes enormous compared to a distant observer. A clock close to the horizon ticks slower relative to one far away. If you were hovering near a black hole and you could somehow survive the radiation and tidal forces and general hostility, you would experience your own time normally. Your heart would beat, your thoughts would drift, your breath would come and go. Your local physics would feel fine, but someone far away, watching you with a telescope, would see your motion slow down. They would see your clock tick more and more slowly. From their perspective, you would never quite cross the horizon. You would fade, red-shifted, your signals stretched into longer wavelengths, like the universe smearing you into darkness. From your perspective, you would cross in a finite time. The horizon is not a physical wall. It is a boundary in space-time. You pass it, and the rest of the universe becomes less able to communicate with you, which is a polite way of saying you have left the chat. But we do not need to ride black holes tonight. We only need to know that the same rule applies everywhere. Gravity changes clock rates. Speed changes clock rates, and both do it in a way that is predictable, tested, and quietly relentless. All of this can sound like a trick, so let us ground it in something comforting. How the universe keeps its rules straight, even when time bends. The first comforting thing is that inside your own frame, you always feel normal. Your biology does not become surreal just because you are moving. Your chemistry does not become confused because you are high on a mountain. Your cells do not hold meetings about relativistic corrections. This is because the laws of physics are local. In your immediate neighborhood, in a small enough region of space-time, things behave in a familiar way. Your clock measures your proper time, and your body follows it. Cause and effect still works locally. You cannot watch your own time slow down because any process you use to measure time is slowed along with you. Your thoughts are not outside the system. They are part of it. This is why time dilation can be both real and unnoticeable. It is real in comparison. It is invisible in isolation. The second comforting thing is that light acts like a universal referee. The speed of light in vacuum is the same for all observers. This is not just a quirky fact. It is the spine of relativity. Because light speed is fixed, space and time are linked. If you move faster through space, you move differently through time. Not like a conscious choice, but like a constraint. There is a kind of conservation here, not of time alone, but of space-time intervals. A metaphor, gentle and imperfect. Imagine you have a fixed budget to spend on two things, distance and duration. You cannot increase one without adjusting the other. The universe keeps the ledger balanced, and it does not accept overdrafts. This is why time dilation is not a bolt-on feature. It is stitched into the structure. If you try to ignore it, your predictions break. Your GPS fails. Your particle experiments disagree with you. Reality becomes petty and refuses to cooperate. And since we mentioned particles, we can take a calm glance at a place where time dilation is not just a philosophical idea, but something that keeps certain particles alive longer than they should. High in the atmosphere, cosmic rays smash into molecules and create showers of particles, including muons. Muons are like heavier cousins of electrons. They are unstable. They decay quickly. In their own rest frame, they have a short lifetime, only a few millionths of a second. Given that, you might think muons created high in the atmosphere would decay before reaching the ground. And many do. But a surprising number reach detectors at Earth's surface. They survive longer than you would expect if you used only their rest lifetime and a simple travel time. Time dilation explains it. From our ground frame, the muons are moving very fast. Their internal clocks run slower relative to us, so their decay is delayed in our frame. They live long enough, from our perspective, to reach the ground. From the muon's perspective, its clock runs normally. What changes is the distance to the ground. Length contraction, another relativistic effect, makes the atmosphere appear thinner in the direction of motion. The muon sees less distance to travel. Either way, the combined rules agree. The universe keeps its story consistent. This is the theme. Relativity is not a pile of disconnected weird tricks. It is a single coherent framework, and it stays coherent no matter who is moving. Now, once you accept that each traveler carries their own calm now, the next step is to imagine how different nows fit together. This is where simultaneity starts to soften. Simultaneity is the idea that there is a universal slice of the universe called now, where things happen at the same time. In everyday life, that is a useful fiction. You and a friend can say, "Meet me at 9, and you will both arrive in roughly the same era of existence. The Earth is small enough, and your speeds are slow enough that you can pretend now is shared." But in relativity, simultaneity depends on the observer. Two events that seem simultaneous to one observer may not be simultaneous to another who is moving relative to the first. This sounds like a logic trap, but it is more like a geometry fact. Different observers slice space-time into space and time in different ways, and their slices are tilted relative to each other. A calm, relatable analogy is thunder. Lightning flashes far away. Two people stand at different distances. One hears the thunder first, the other hears it later. They do not argue about whether the lightning happened. They only have different arrival times for the sound because of distance. With light, you might think it should be simpler because light is fast. But in relativity, light speed is constant, so you cannot just correct it away with one universal time. Observers in relative motion disagree about which distant events are happening now because the light signals they use to define now arrive differently, and the geometry demands it. There is a classic thought experiment with a train again, because trains are the unofficial mascot of relativity. Imagine lightning strikes the front and the back of a moving train. An observer standing on the ground at the midpoint between the strike points might see the flashes arrive at the same time and declare the strikes simultaneous. But an observer on the train, also at the midpoint of the train, is moving toward one flash and away from the other. Because light speed is the same, the observer on the train receives one flash before the other and declares the strikes not simultaneous. Nobody is hallucinating. Nobody is broken. They are using consistent rules, and the universe allows both descriptions. Because the concept of distant simultaneity is not absolute. This is where you might feel your brain try to sit up in bed and demand to speak to a manager. You can let it relax. The key is this: relativity does not say everything is subjective. It says the structure of space-time is objective, and different observers decompose it differently. There are quantities that everyone agrees on, like the space-time interval between events. But the split into what is purely time and what is purely space depends on motion. If that feels too abstract, bring it back to something simple. Your experience of now is local. It is defined by what can influence you, and what you can influence by signals traveling at finite speed. You do not have access to the entire universe at once. So, the universe does not owe you a universal now. It is a quiet, humbling thought. The cosmos is not centralized. There is no master clock that the galaxies synchronize to, like a network time protocol server in the sky. Each region has its own proper time, its own local rhythm. And yet, physics remains coherent. Causality remains intact. You cannot send information faster than light. You cannot create effects before causes in your own frame. The universe prevents the worst kinds of paradoxes by enforcing light as the speed limit for influence. So you get this strange compromise. Time is flexible, but not chaotic. Relative, but not arbitrary. Personal, but still bound by shared laws. And that is a good place to pause for a moment, because we have covered the basic machinery. We have taken a second and demoted it from cosmic law to counted rhythm. We have watched motion stretch time and gravity weigh it down. We have seen satellites live slightly different clock lives, and we have let simultaneity become a softer concept. In a moment, we can take these ideas and explore them more gently, looking at how two clocks can disagree without anyone being wrong, and what it really means to take different paths through space-time, like taking different roads through the same dark city. But before we widen the view, let us stay with the simple idea of two clocks separated and reunited, and why the universe calls that perfectly fair. Because the clocks are not arguing about time as an idea, they are reporting what happened along their own world lines, their own stitched paths through space-time. If you want the cleanest version of this, you do not need a spaceship or a black hole or a physicist with wild hair. You just need 2 clocks, a separation, and patience. One clock stays with you, on the table, under the same ceiling fan that has been making that low, tired whir for years. The other clock leaves. It goes somewhere else, does something else, moves through a different pattern of motion and gravity. Then it comes back, and the two are placed side by side again. They are now in the same place at the same time. And you can finally do the thing humans love to do: compare numbers and feel either vindicated or betrayed. The clocks show different elapsed times. And the important part is this: the difference is not an opinion. It is not about perspective in the casual way. It is a physical difference in accumulated proper time, the time each clock actually lived through. In relativity, a clock is not just a device that measures time. A clock is any physical process that advances step by step. A swinging pendulum, a quartz crystal vibrating, a cesium atom flipping its energy state, your heartbeat, your cells repairing DNA damage, one small correction at a time. If time dilation is real, it can not only affect clocks in the narrow sense, it has to affect everything. If it only affected the clock display, it would be a cheap magic trick, but it affects the atom itself, and the chemistry in your body, and the decay of particles, and the rhythm of electrical signals in neurons. So, when two clocks disagree after traveling different routes, it is not that one of them got confused, it is that the universe gave them different lengths of time to spend, because they took different paths through the geometry. This is why the twin story is not actually about twins. It is about paths. Twins are just a dramatic prop because humans care more about faces than about space-time diagrams. One path is simple, mostly sitting still in one frame. Another path involves high-speed travel, or different gravitational depths, or both. When the two travelers reunite, the paths have different proper lengths in time. The reunion is the comparison point where you can finally see the difference. There is a quiet fairness to it, not a moral fairness. The universe does not do morals. A geometric fairness, like two people walking across a city, one taking a straight route, one wandering through alleys, bridges, and stairwells. They meet at the same cafe, but one has been walking longer. Both are telling the truth about their own feet. Now, you might wonder why this is allowed to happen at all. Why can the universe not just keep everything synced? Why not enforce one master time the way a tired manager enforces one shared schedule? Because the speed of light is the manager, and it is not flexible. Light does not speed up because you are late. It does not slow down because you are nostalgic. It has one speed in vacuum for everyone. That single stubborn rule forces the rest of spacetime to rearrange itself so no observer can measure light doing anything else. And that rearrangement shows up as time dilation, length contraction, and the relativity of simultaneity. Not as separate gimmicks, but as the same rule seen from different angles. So the universe is keeping its rules straight by doing the opposite of what your intuition wants. It does not enforce one universal time. It enforces one universal causality structure, one consistent way that signals and influences can flow. Time becomes local because influence is local. That is the deep comfort hiding under the weirdness. Even when seconds stretch, cause and effect still has teeth. You cannot casually rearrange the order of events that can affect each other. The universe will let distant now get fuzzy, but it guards the boundaries of what can physically happen. Because physics is not interested in letting you send a message to yesterday. If you want to ground this again in something less philosophical and more mechanical, go back to the light clock. 2 mirrors, a pulse bouncing, a tick in its own rest frame. It is as simple as a metronome. The light travels a fixed distance between the mirrors, so the time between ticks is steady. But if the clock moves relative to you, you see the light take a longer diagonal path. Light still moves at the same speed, so the time between ticks gets longer. That is special relativistic time dilation. Now imagine a clock sitting deeper in gravity. A clock at sea level compared to a clock on a mountain. Gravity changes the geometry of space-time, so the relationship between coordinate time and proper time shifts. The deeper clock accumulates less proper time compared to the higher clock, and you can interpret that as the deeper clock running slower. But what it really means is that the space-time metric, the rule book for measuring intervals, assigns different proper time lengths to different locations. You do not need the equations tonight, but it helps to know there is a rule book, not a vibe. The rule book has been tested in laboratories, in aircraft, in satellites, in particle beams, in signals passing near the sun. It is not folklore, it is infrastructure. And once you accept that, the 2 clocks stop being a paradox. They become a measurement, a quiet survey of space-time. There is a famous real-world version of this, because physicists have always been the sort of people who look at a profound truth and immediately ask, can we put it in a suitcase? In the early 1970s, researchers flew atomic clocks on commercial airliners around the world and compared them to clocks that stayed behind. The flying clocks came back offset by tiny amounts, exactly in line with relativity once you include both motion and gravity. It is one of the most understated flexes in science. You take a clock that counts the tremble of atoms, put it on a plane with stale cabin air and a screaming baby, and it returns with proof that space-time is not flat and time is not universal. Congratulations! You have just turned economy seating into an experimental test of the structure of reality. But hey, that is thermodynamics for you, and also aviation. Now, there is a question that usually follows, and it is one of those questions that sounds innocent but can keep you awake. If time depends on motion and gravity, what is really happening? Is time actually slowing, or are clocks just being affected? Think again. A clock is not a separate thing from time. Time is what a clock measures, and a clock is a physical process. If every physical process in that environment experiences the same shift, then the only meaningful statement is that proper time itself is different. In other words, the universe is not reaching down to mess with your watch. The universe is telling you that your path through space-time has a different time length than another path. The watch is just the part that is honest enough to admit it. If you are still tempted to imagine a universal background time that everything is really moving through, you can, as a private hobby. But physics does not need it. Physics runs cleaner without it. In relativity, the closest thing to really is the invariant space-time interval, the thing all observers can compute and agree on. That invariant interval is like the bedrock. The split into time and space is like the furniture arrangement. Different observers arrange it differently, but the floor plan is the same. This matters because it explains how the universe can be flexible without being chaotic. Your coordinates might change. Your notion of what is simultaneous might change, but the underlying structure remains consistent. And that consistency is what keeps the whole thing from collapsing into nonsense. Now, you might be wondering what stays steady in your own experience. If seconds are negotiable, what is the anchor? Your anchor is your proper time, your local clock, the time measured along your world line by the processes in your own body, inside your own frame. Your physiology does not feel like it is moving through syrup. Your neurons fire, your muscles respond, your stomach digests with the same unglamorous commitment. If you are tired at one subjective speed, not slowed down by the fact that you are on a fast ship. This is why astronauts on the International Space Station do not feel like they are living in slow motion. They are moving quickly, and they are higher in Earth's gravity field, so their time rate differs slightly from people on the ground. But their whole internal system is consistent. They still have to do chores, still have to sleep, still have to wipe down surfaces to keep mold from becoming a new crew member. The dilation is real, but it is external in the sense that it shows up when you compare across different paths. Locally, life is life. Now, since we have brought up the International Space Station, it is worth noting something quietly funny. Time dilation is happening to you right now, even if you have not left your bed. You are rotating with Earth. You are moving through space as Earth orbits the Sun. The Sun orbits the galaxy. The galaxy moves relative to the cosmic microwave background. Everyone is moving relative to something. There is no final state of rest. There is no universal couch where the universe sits down and stops. So the question is never, are you time dilated? The question is, compared to whom and by how much? At Earth's surface, the amounts are small, but they are not zero. And if you had a clock precise enough, you could map time dilation across the landscape. You could draw contour lines of proper time rate like a weather map. Time as a kind of topography. In fact, people do something close to this. Modern atomic clocks are so precise that moving one by a few centimeters in height can produce a measurable frequency shift because of gravitational time dilation. That is a sentence that should make your ancestors feel faint. A few centimeters. Not a mountain, not a plane. Just lifting a clock by the thickness of a paperback book, and the rate changes enough to detect? The good news is, reality is consistent. The bad news is, reality has no respect for what feels too small to matter. This ability opens a whole field sometimes called relativistic geodesy, where you use precise clocks to measure gravitational potential differences, and therefore infer information about Earth's shape and mass distribution. In other words, you can use time itself as a sensor for gravity. A clock becomes a kind of gravitational probe. Congratulations, you have just turned "what time is it?" into "what is the density of the crust beneath my feet?" But hey, that is general relativity for you. Now, earlier we touched on what stays steady, and one of those steady things is the speed of light. But there is another steady structure that matters for sleep-friendly understanding: the light cone. A light cone is not an object. It is a way to classify events. For any event, like you snapping your fingers, there are events that can be influenced by that snap, and events that can influence it, given the finite speed of light. The set of all possible future events you can influence forms a region in space-time, bounded by light signals. That boundary is the future light cone. The past light cone is the region of events that could have sent signals to reach you at that snap moment. Everything outside those cones is elsewhere, in the sense that there has not been enough time for any signal to connect the events. Different observers may disagree about the time order of some of those elsewhere events. That is the relativity of simultaneity doing its soft sabotage. But everyone agrees on the causal structure. Everyone agrees that you cannot influence outside the future light cone without breaking the speed limit. That is the guardrail. So when you hear that simultaneity is relative, the soothing correction is yes, but causality is not casually violated. The universe is weird, but it is not sloppy. Now, you can take that structure and understand why the twin story works. The traveling twin and the stay-home twin follow different world lines. The proper time along each world line differs. When they reunite, that difference is invariant. Everyone can calculate it and agree, even if they disagree on intermediate slices of simultaneity. It is like two hikers taking different trails to the same cabin. They can argue about which trees they passed at what moment, but the length of the trail they each walked is what it is. When they compare pedometers at the door, the numbers do not care about opinions. Now, we have talked gently about clocks and paths, and we have tasted the extremes, fast ships and black holes. But there are more places where time dilation shows up in a way that is almost soothing, because it is so consistent and so repetitive. One of those places is particle accelerators. In a circular accelerator, particles are whipped around near the speed of light, held in their curved path by magnets, forced to loop again and again like tiny unwilling commuters. These particles, like muons and other unstable species, have lifetimes in their rest frame. But in the lab frame, because they are moving so fast, their internal processes are time dilated. They live longer. From our perspective, this is not a metaphor. It is measured. It is part of how accelerators work and how we interpret the data. If you ignored time dilation, your predicted decay rates would be wrong. Your detector counts would not match. You would be forced, reluctantly, to believe in it. The same thing happens with cosmic rays, as we mentioned, but accelerators make it controllable. The laboratory becomes a place where time dilation is turned into a tool. And there is a strange intimacy to that. You take a particle that would normally vanish in microseconds, and you stretch its life not by coddling it, but by throwing it through space-time at a speed that makes time behave differently. It is not kindness. It is geometry. Now, time dilation is usually explained as a slowing of time for moving objects, but it can be helpful to hold a more symmetric view. In special relativity, if two observers move relative to each other, each can describe the other's clock as running slow. That seems like a contradiction until you remember they are slicing space-time differently. They disagree about simultaneity. So if you are on the train, you can say the platform clock is slow. If you are on the platform, you can say the train clock is slow. Both statements are correct within each frame's definition of at the same time for distant clocks. This is why the reunion is so important. When the clocks come back to the same place at the same event, the comparison becomes local. There is no more distant simultaneity to argue about. The difference in proper time is a single number everyone must accept. The twin story forces a reunion by turning the traveling twin around. The turnaround introduces acceleration, which breaks the symmetry. That is where a lot of people get tangled because they want acceleration to be the cause. But the deeper cause is still the difference in space-time paths. The acceleration is part of what makes the paths different. If you want a calmer image, imagine one clock stays at home. Another clock takes a long trip with changes in speed and direction, then returns. The traveling clock has traced a bent world line, a path that is not straight in space-time. And in relativity, straight paths, inertial paths, often maximize proper time between two events in flat space-time. The bent path accumulates less, so the traveling clock is the one that ends up behind. Not because motion is morally punished, but because the geometry works out that way. Now, gravity complicates that picture because space-time is curved, and straightest possible paths become geodesics in curved geometry. In a gravitational field, a free-falling path is a geodesic. That means something that feels counterintuitive at first. Sitting still on the ground is not inertial. You are being accelerated upward by the ground. Even if it feels like rest, your feet are being pushed up by the floor. The floor is refusing to let you fall. Your body is in a constant state of tiny stress. That is what weight is. The electromagnetic resistance of atoms in the ground pushing against the electromagnetic structure of atoms in you. So in general relativity, a person in free fall is more at rest than a person standing still on Earth. This is why astronauts in orbit feel weightless. They are not outside gravity. They are in free fall around Earth. They are following a geodesic. And this is part of why gravitational time dilation is not just about gravity pulling on clocks. It is about the geometry of space-time and the difference between accelerated and inertial motion. Now, if you combine speed and gravity, you can get situations where clocks do surprising things relative to each other. For example, a clock on a satellite is moving fast, which tends to slow it down relative to Earth, but it is also higher up in weaker gravity, which tends to speed it up relative to Earth. For GPS satellites, the net effect is that the weaker gravity wins, so the satellite clocks run faster than ground clocks by a small but significant amount, on the order of tens of microseconds per day. Tens of microseconds does not sound like much, but light travels about 300 meters in 1 microsecond. So a timing error of tens of microseconds translates into kilometers of position error. That is why the corrections are mandatory, not optional. If you are lucky, the navigation error kills your road trip before your patience does. And the corrections are not just set once. The satellite's orbits are not perfect circles. Their speeds vary slightly. Their altitude varies. Earth's gravity field is not perfectly uniform. Solar radiation pressure nudges them. The moon tugs. The sun tugs. So the system constantly updates using control segments on the ground that monitor and adjust the time signals. This is one of those rare moments where relativity leaves the textbook and becomes a service you rely on to find a quiet place to buy antacids at 1 in the morning. Now, since we are talking about practical uses, there is another application that is not as famous as GPS, but is quietly everywhere. Time synchronization in networks, financial transactions, power grids, telecommunications, all rely on precise timestamps. And as clocks become more precise, relativistic effects become less ignorable, even over short distances. If you have two data centers at different elevations, the gravitational potential difference can introduce a measurable drift over time. If you are operating at the edge of precision, it is not that your laptop is going to crash because you moved it upstairs. It is that the most extreme precision systems, the ones that care about nanoseconds, have to treat Earth as a relativistic object, not a flat map. Again, reality is consistent. Reality is also inconvenient. Now, let us return to the bigger picture, the one that makes time feel like a landscape. If time is a landscape, then moving fast is like taking a path that tilts your time axis. Gravity is like a valley where the slope changes the rate at which time accumulates. In this landscape, there is no single now that blankets the entire terrain. There are local nows, like little patches of fog that each traveler carries. When we talked about simultaneity earlier, with the train and lightning, we were describing how different observers slice space-time differently. That is the gentle mismatch of many nows. You could make it even more intuitive by thinking about how we define distant simultaneity in practice. If you want to say two distant clocks are synchronized, you need a procedure. One common procedure in Einstein's original framing is to send a light signal from clock A to clock B, reflect it back, and assume the light travel time is the same in both directions. Then you set the clock so that the event at B is assigned the midpoint time between emission and reception at A. That is a reasonable convention. But the key word is convention. It relies on assumptions about symmetry in the signal travel, and it depends on the frame you are using. In a moving frame, the midpoints differ, so different observers can have different synchronization schemes that are internally consistent. This is not just philosophical hair-splitting, it is the operational basis of why simultaneity becomes relative. If you define now by synchronized clocks, and synchronization depends on motion, then now depends on motion. The universe is not being poetic. It is being procedural. Now, there is another way to think about this that can be very calming. Instead of imagining the universe as a film reel with one frame called now, imagine the universe as a block, a four-dimensional structure where events simply are. Past, present, future, all part of the geometry. In that view, your experience of time is like moving along your world line through this block. You do not experience the whole block at once because your brain is a physical process that unfolds step by step. Different observers have different directions of time through the block, different ways of slicing it into space plus time. That is why they disagree about simultaneity. This block universe perspective can be unsettling if you treat it like fate, but physics does not require you to interpret it that way. It is a description of space-time as a whole, and it can be soothing because it removes the idea that time is a fragile thing that might break. It is more like geometry. You cannot panic a triangle into having four sides. Now, before your mind tries to take that too far, bring it back to the body. Your lived reality is still your lived reality. Your decisions still happen. Your uncertainty about tomorrow is still honest because you do not have access to the full structure. You are inside it. Relativity changes how we describe time. It does not give you the keys to the universe's locked filing cabinet. Now, there is one more subtle point that often makes people restless. If time dilation is real and observers disagree about rates, does that mean there is no objective aging, no objective time passage? There is objective, proper time along a world line. That is the time your body experiences. Two different world lines between the same events can have different proper times. That difference is objective. So there is no universal time that everyone shares, but there is still a very real sense in which each traveler has a clock that measures their own time. And those clocks can be compared at meetings, reunions, collisions, and any other event where world lines cross. Physics becomes a story about meetings, about intersections. Now, if you want a slightly more visceral image, because the Sleepless Scientist cannot resist making it physical, imagine you could smell time dilation. Not as a fragrance, more like the sharp bite of ozone after a lightning strike, something that tells you the air has been electrically rearranged. In a fast-moving ship, you would not smell anything different because your nose and your neurons are inside the same slowed proper time. The chemistry of scent reception is slowed with everything else. But when you return and compare, the mismatch would feel like jet lag without travel, like stepping into a room where everyone has aged a little more than you. Their faces have moved forward by a small fraction of a year. Yours has not as much. No glow, no shimmer, just a quiet accounting difference. The universe does not do special effects. It does bookkeeping. Now, we have been gentle with the lack of math, but it can help to know one basic shape of the special relativistic time dilation relationship. The time dilation factor depends on your speed relative to the speed of light. The closer your speed gets to light speed, the larger the factor becomes. At low speeds, it is almost 1, meaning almost no dilation. At high speeds, it grows noticeably. As you approach light speed, it blows up, meaning time dilation becomes extreme. This is why you cannot reach the speed of light if you have mass. You would need infinite energy. The universe has decided that light speed is reserved for things that do not have rest mass, like photons. Everything else has to settle for less, no matter how much fuel it throws at the problem. If you want to think of it as a speed limit, it is not like the speed limit on a highway, where the sign is mostly a suggestion. It is a structural limit of space-time. It is the limit of how fast cause and effect can propagate. Now, general relativity gives a similar relationship for gravitational time dilation. The deeper you are in a gravitational well, the slower your proper time runs relative to far away. Near Earth, the differences are small. Near neutron stars and black holes, they become huge. A neutron star is what you get when a massive star dies and its core collapses. The protons and electrons are crushed into neutrons, and you end up with a sphere about the size of a city, but with a mass greater than the sun. The gravity at its surface is violent. The tidal forces are intense. If you stood on it, which you cannot, you would be pinned and shredded in a way that makes all your earthly worries seem charmingly irrelevant, and time near its surface would run slower compared to far away. If you had a clock near the surface and a clock far away, the near one would lag behind. It would accumulate less time. Again, not as a feeling, but as a comparison. Black holes take this further. Near the event horizon, time dilation relative to far away can become arbitrarily large. Signals climbing out of the gravity well are redshifted, stretched. The far observer sees the near horizon clock slow and fade. This is why black holes are often used in science fiction as time machines. You go near one, come back, and the universe has aged. That part is loosely based on the geometry. The part they skip is that the environment near a real black hole is usually full of hot plasma, intense radiation, and tidal forces that would rearrange your body into a long, thin problem. Forget what you saw in Interstellar. The truth is, you would be very busy becoming debris, but the concept remains useful as an extreme illustration. Gravity can slow time. Speed can slow time. And in the right conditions, the difference can be large enough to matter in a human sense. Now, one last grounding point before we drift further into simultaneity again. If you are moving relative to me, and I say your clock is slow, that does not mean I am saying you are doing something wrong. It means the geometry between our frames demands that I assign your ticks a larger time interval when I describe them. And you can say the same about me. This mutual time dilation is not a conflict because the comparison of distant times depends on simultaneity. And simultaneity is not shared. It is only when you bring the clocks back together that the comparison becomes unambiguous. So, the safe way to talk about who really experienced less time is to talk about reunions and intersections. That is why the traveling twin is younger at the reunion. Not because one frame is correct, but because the traveling twin took a different path that contains less proper time between the departure and reunion events. Now, you might ask, what if both twins travel in different ways and meet again? Then both could be younger than a third person who stayed behind, and their relative ages would depend on their paths. This is not a paradox. It is a map problem. Time is not a single river. It is more like many small streams running through a terrain, joining and separating, with different slopes, and your body is a leaf on one of those streams, carried along by the local geometry. We will keep going from here because there is still a lot of quiet weirdness left, especially in how many nows fit together and how the universe stays coherent without a centralized clock. But for the next stretch, keep the picture simple. 2 clocks, 2 journeys, 1 reunion. The universe is not unfair, it is just not centered on you. So let us keep centering it on paths, because paths are something you already understand with your bones. A path is not just where you go, it is how you go. It includes your speed, your turns, your weights, your climbs. In space-time language, it is your world line, the stitched thread of your existence, event by event. And the universe is very literal about it. It does not care what you meant to do. It cares what you actually did. If one clock rides a smooth, constant speed journey, and another clock keeps stopping, turning, accelerating, or sitting deeper in gravity, those are different world lines. They are different shapes through space-time. When you reunite, the clocks are just reporting the geometry. The quiet part people miss is that time dilation is not something added on to time. It is time behaving like a measured distance. It is the length of your path, but in the time direction. In flat space-time, without gravity, the straightest world line between two meetings tends to maximize proper time. That means, in a very specific relativistic sense, doing nothing dramatic is often the way to experience the most time, which is an unexpectedly validating message for anyone lying down at night, not moving, not traveling, not attempting to outrun their own calendar. The universe is basically telling you, yes, staying home is a high, proper time lifestyle. But then gravity shows up and ruins the simplicity, like it ruins everything. Because in curved space-time, the straightest paths are not obvious by intuition. A free-fall path is straight, a geodesic, even if it looks curved in space. Orbit is a kind of continual falling. So the person floating in orbit can be more inertial than the person standing still on the ground. And that leads to one of those soft reversals. The good news is, you can say with a straight face that standing still is not truly rest. The bad news is, it means your floor is accelerating you all day long. You can feel that acceleration as weight. Weight is not gravity tugging you downward. Weight is the ground pushing you upward, denying you the free fall you would otherwise do. Your atoms are pressed together. The electromagnetic structure in your shoes and bones is resisting collapse. It is a quiet, mechanical stress you are so used to, you call it normal. So when we talk about clocks on the ground and clocks in orbit, we are comparing different combinations of speed and gravitational potential, and also different states of acceleration. This is why the International Space Station is a nice bedtime example. Not because it is relaxing, it is a metal can full of filters, sweat, and recycled air, but because it sits right in the overlap of effects. The station is moving fast, so special relativity says its clocks run a little slow compared to Earth. But it is also higher up, so general relativity says its clocks run a little fast compared to Earth. The two effects mostly cancel, but not perfectly. Depending on the orbit and details, astronauts end up aging a tiny bit less than people on the ground. It is not enough to dodge a birthday, but it is enough to measure if you are the kind of person who owns an atomic clock and has no fear of being unpopular at parties. And that is a theme worth keeping because it makes the universe feel less like a trick. Whenever you hear that time is slower here and faster there, remember it is a comparison. It is always relative to some chosen reference. Your experience is locally normal, and the accounting differences only show up when world lines cross again. Now let us move from paths to something that sounds more philosophical, but is really about bookkeeping. The question of many nows. Because even if you accept that clocks can disagree, your mind still wants a universal moment, a master now, a cosmic refresh button. You want to believe that somewhere the universe has a current frame and all events are either present or not. It is a deeply human craving, probably built from living on a planet where most things happen slow enough that the fiction works. But once you start coordinating fast movers or far distances, that fiction becomes expensive. Here is a way to feel it without equations and without train lightning, because we have already used trains as our emotional support vehicle. Imagine you and a friend are far apart, sitting in separate rooms, each with a very good clock. You want to agree on when to start playing the same song exactly together. So, you do the practical thing. You try to synchronize clocks by sending signals, light signals, or radio signals, because those travel at light speed. You send a ping. Your friend receives it. They send a reply. You measure the round trip time, and you assume the one-way trip is half of that. That assumption is not a law of nature. It is a convention, a reasonable one, but still a choice. It assumes the signal took the same time going and coming back. In a frame where you and your friend are at rest together, that convention behaves nicely. In a frame where one of you is moving relative to the other, the geometry gets awkward. The midpoints change. And because light speed is fixed, you cannot fix it by saying, well, we will just correct for motion the way we correct for sound delay. With sound, the air is a preferred medium. With light in vacuum, there is no preferred medium. That is the entire point. So when you define now across distance by synchronizing clocks, your definition depends on your state of motion. Another observer, moving relative to you, uses the same procedure and gets a different slice of simultaneity. Different events get grouped into their now. The good news is, nobody is wrong. The bad news is, the universe does not provide a single, global timestamp. To keep it grounded, think of it like trying to draw straight latitude lines on a lumpy planet. You can choose a method. You can make it consistent. But someone else, using a different reference, can draw a different consistent grid. The planet does not care. The planet was not built for your convenience. In space-time, those grids are coordinate systems. And now is a coordinate choice, not a universal substance. This is why relativity tends to cause a certain kind of insomnia. Not because it is complicated, but because it robs you of a comforting, centralized narrative. But it also gives you something back. It gives you a cleaner concept of what is truly real in the theory. What is real, in the sense that everyone can agree on, is not your distant now. It is what can causally affect what. It is the structure of light cones. It is the space-time interval between events. It is proper time along a world line. Those are the invariants. Those are the bedrock. Your slice of simultaneity is like a personal preference in furniture layout. The invariants are the load-bearing beams. Now, since we are already standing in the room of many nows, let us step carefully into something that sounds abstract, but can be made gentle. In special relativity, when you draw a space-time diagram, time is one axis and space is another. Your world line is a line on that diagram, and light rays make 45-degree lines because light is the standard. Different observers tilt their axes relative to each other, not because the universe is spinning, but because their definitions of time and space mix when they are in relative motion. That tilt is the mathematical way of saying, you and I disagree about what counts as purely space and what counts as purely time. We carve up the same four-dimensional reality differently. So when you ask, which events are happening now, you are really asking, which line across the space-time diagram counts as my present? And that line depends on the tilt. It is not a feeling. It is geometry. This is where the train lightning story comes from. But you can replace the train with anything moving. A plane, a satellite, a drifting ship. If you are moving toward a distant event, you meet the light from it sooner. If you are moving away, you meet it later. Because light speed is fixed, the only way to keep consistency is to allow different observers to disagree about the time ordering of distant, causally disconnected events. Causally disconnected is the soothing part. It means neither event can influence the other without faster-than-light signals. So the order is not physically meaningful for cause and effect. The universe is basically saying, if nothing can connect them, then you do not get to demand a single universal order. You get your local cause and effect. Distant elsewheres are allowed to be slippery. Now, if you want to feel the edges of that slipperiness, consider a strange but calm scenario. 2 fireworks go off, far apart in space, so far apart that light from one cannot reach the other before the other happens. There is no causal link. They are space-like, separated. One observer moving one way says, the left firework happened first. Another observer moving another way says the right firework happened first. You might think that means reality is contradictory, but nothing breaks because no information, no influence, no physical consequence depends on that order. The fireworks are isolated events. The universe does not owe you a ranking. Where the universe becomes strict again is when there is a causal connection. If one event can influence another, the order is fixed for all observers. Cause stays before effect in every frame. That is the hard spine under the soft surface. This is why light cones matter. They separate the physically meaningful orderings from the coordinate-dependent ones. Now, a small pattern interrupt. Because we have been polite and philosophical for a while. Congratulations! You have just tried to schedule the universe like a group chat. The universe has left you on read. But it is not cruelty. It is just physics refusing to provide services it cannot provide without breaking its own rules. Now, there is an even calmer way to think about many nows. One that feels less like losing control and more like gaining a map. Instead of thinking of the universe as constantly updating like a screen, refreshing, think of it as a 4-dimensional structure and your consciousness as a process moving along one thread. This is the block universe picture. It is not the only interpretation, and you do not have to make it into a spiritual doctrine. It is simply a way to visualize what relativity is already telling you. In that picture, the set of all events exists as a geometry. Your past is a region of that geometry. Your future is a region. Your now is not a universal plane. It is a local experience as your brain processes signals arriving at your senses. Different observers carve different 3-dimensional slices through that 4-dimensional structure and call those slices now. But the structure itself is the same. The good news is the universe becomes less mysterious. The bad news is it becomes less personal. And that is why it can actually be good for sleep listening. It is humbling in a way that does not demand action. It is a reminder that your insomnia is not a cosmic emergency. The cosmos does not have emergencies. It has metrics. Now, since we have been talking about slicing space-time, it is a good moment to revisit something practical. When engineers build systems that involve moving clocks and distant timing, they cannot afford vague nows. They have to choose a coordinate time, a reference frame, and define synchronization procedures. They have to make a convention and then stick to it. For Earth-centered systems, they often choose an Earth-centered inertial frame, or something close, and define a coordinate time that is convenient for satellites and ground stations. Then, they apply relativistic corrections to keep the coordinate system coherent. because the actual clocks are experiencing different proper times. So your navigation works not because time is simple, but because humans chose a standard time coordinate and then paid the correction fees. The universe charges interest, and the interest is microseconds. Now, let us go back to the idea of extreme places for a moment, but keep it gentle, not cinematic. We already mentioned black holes and neutron stars, but there is a simpler extreme that does not require cosmic horror. It only requires speed and patience and a destination far away. Imagine a ship that can travel at 90% of the speed of light, not 100%, because you cannot have that. Not with mass, but 90% is already enough to make time do noticeable things. From the point of view of people back home, the ship is moving fast and its clocks are slowed, so the travelers take longer to reach the destination in home time, but they experience less time on board. From the traveler's point of view, their time feels normal, but distances in the direction of motion are contracted, so the universe looks squished in the direction they are traveling. The trip feels shorter in distance and thus shorter in time. The beauty, if you want to call it that, is that both descriptions agree on what happens when the travelers return and compare clocks. The travelers have aged less. This is not just a story. It is the same mechanism that lets muons reach the ground and that lets particle beams live longer in accelerators. The universe is already running these experiments for free in the upper atmosphere. In every cosmic ray shower, humans only imitate it with expensive machines and grant proposals. Now, there is a detail we have carefully avoided because it tends to wake people up. But we can touch it lightly. In special relativity, time dilation and length contraction are linked. If you try to keep only time dilation and ignore length contraction, you break consistency. If you keep both, the universe stays coherent. This is why the muon story is so satisfying. From our frame, the muon lives longer. From the muon frame, the distance is shorter. Both lead to muons arriving at the ground. It is like the universe giving you two different accounting methods that still reconcile at the end of the fiscal year. But hey, that is corporate mandated physics for you. Now, let us widen again, because the outline we are following wants us to stay with what remains steady when time changes, and then move into many nows. We have already started many no's, so let us anchor it again with what stays steady. First, locally, your laws of physics. If you are in a sealed spaceship coasting at constant velocity, you can do experiments inside. You can drop objects, you can shine lasers, you can measure atomic transitions, and everything behaves normally. You do not get a blinking warning light that says, "You are currently time dilated." No sirens, just regular physics, because in your frame, you are at rest. This is a principle, sometimes called the principle of relativity, and it is one of the reasons special relativity is not optional. The laws of physics are the same in all inertial frames. There is no special frame where the universe is really at rest. Second, the speed of light. You can be moving. I can be moving. We can both measure light speed in vacuum, and we both get the same answer. That is the stubborn spine. Third, the space-time interval. If two events happen, everyone can compute the interval between them, and they agree. They may split it into different amounts of space and time, but the combined structure stays the same. That is what invariant means here. Proper time is part of that. Proper time along a world line is an invariant for that traveler. Everyone agrees how much proper time the traveler experienced between two crossings, even if they disagree about intermediate coordinate times. So when time feels flexible, it is not because the universe is sloppy. It is because the universe has a deeper structure than the one your brain grew up assuming. Now, if you want one more physical body-based image to hold on to, use your heartbeat. Your heartbeat is a clock, not a good clock, not an atomic one, but it is a rhythm. If you are on the fast ship, your heart beats normally by your own measure. Your blood still tastes like iron. Your lungs still feel like lungs. You still get hungry. You still feel boredom. Congratulations! You have carried your metabolism into relativistic kinematics. From Earth, watching you, your processes look slowed. They would say your heart is beating slower, but it is not inside your frame. It is only slower when described in their coordinate time. And when you return, you might find Earth has aged more. Your friends have more wrinkles. Their hair has shifted. Your favorite late-night diner has rebranded twice and now sells only artisanal oat milk soup, because time is cruel in non-relativistic ways too. The key is, nobody was living in slow motion from their own perspective. That is the calm truth. Now, since we have already been circling simultaneity, let us bring in one more piece of it, a thing that is quietly important and often missed. Relativity of simultaneity is not just about distant events. It also affects how you interpret synchronized clocks in motion. If you have a row of clocks along a moving train synchronized in the train frame, they are not synchronized in the ground frame. The ground observer sees the front clock and back clock out of sync by a small amount depending on speed and separation. This is not because the clocks are faulty. It is because the definition of synchronization depends on the frame. And this is why, in special relativity, you cannot have a universal, frame-independent way to say, these distant clocks are all set to the same time. You can do it in one frame and it is coherent in that frame, but another frame will not agree. So when you hear someone say, moving clocks run slow, remember it is tied to how you define simultaneous readings across distance. The moment you make the comparison local, at the same place, the ambiguity disappears. Now, this is a good moment to do one of the gentler paradox dissolves, the kind that feels like smoothing a wrinkle out of a sheet. People sometimes say, if motion is relative, why does the traveling twin end up younger? Why cannot the traveling twin say Earth was moving and thus Earth clocks ran slow? The answer is, during the outbound and inbound legs, each can describe the other as time dilated, but the traveling twin changes inertial frames when turning around. The traveling twin has a different slicing of simultaneity before and after the turn. That change in slicing creates a jump in what the traveling twin considers simultaneous on Earth. In the traveling description, Earth ages rapidly during the turnaround, not because anything physically accelerates on Earth, but because simultaneity planes swing. It is not mystical. It is geometry again. The stay-at-home twin stays in one inertial frame, approximately, ignoring Earth rotation and gravity for the simplified story. The traveling twin does not. So, the situation is not symmetric. You do not have to love that explanation. You only have to notice. It removes the contradiction without adding magic. Now, general relativity adds more layers because gravity makes inertial frames local and temporary. But the principle remains. Proper time depends on the path. And this is why, in the real world, you can have complicated cases where one person moves fast but stays high in gravity, another moves slower but stays deep, and the final comparison depends on the exact details. Time dilation is not a single slider. It is an environment. It is a full context. For example, if you lived on a high mountain, your clock runs faster due to weaker gravity, but you are also moving slightly faster due to Earth rotation being a bit different with radius, though that effect is small compared to the gravitational one for altitude changes. So in practical terms, mountain living makes you age very slightly more over long spans, compared to sea level living. Again, nothing you will notice. But it is a reminder that even the ground beneath you is part of a relativistic system. Now, let us take a slow walk back toward the central weirdness of many nows, and do it with a slightly different angle, one that feels more like everyday experience. Consider something simple, like watching a live broadcast from far away. A spacecraft on Mars sending video back to Earth. When you watch it, you are not watching now on Mars. You are watching what happened minutes ago because the signal took time to travel. Your brain already lives with delayed reality constantly because all information comes with a travel time. Even across your room, light takes a fraction of a second to reach you. So your present is always a stitched-together perception from slightly different moments. You do not notice because the delays are tiny, but the principle is there. So when relativity tells you there is no universal now, part of what it is saying is the universe does not deliver instantaneous updates. There is no omnipresent present moment that everyone shares, because information cannot move infinitely fast. Your now is built from what has had time to reach you. That is a calmer way to accept it. It turns cosmic philosophy into signal travel time, which is something your phone already suffers from daily. Now, the deeper relativity point is that even if you correct for signal delays, different moving observers still disagree about simultaneity because the correction depends on assumptions that differ by frame. But the signal delay story is a good bridge because it makes it less alien. It reminds you that even in everyday life, the idea of a global now is already a useful fiction. Now, there is another place where this matters, and it has a faintly eerie vibe, even when told gently. In astrophysics, when you look at the sky, you are looking back in time. The light from distant stars and galaxies took years, or thousands of years, or millions of years to reach you. So the sky is not a snapshot of the universe. At one time, it is a layered archive of many different times. There is no cosmic now that the sky shows you. The universe you see is a patchwork of pasts. Relativity is the mathematics that makes that patchwork consistent. It tells you how different observers moving differently will slice that patchwork. It tells you how to relate coordinate times to what is observed. The good news is the universe is still coherent. The bad news is it is coherent in a way that does not center your viewpoint. Now, let us do a quiet return to gravity, because gravity is the calmer, heavier lever, and it connects to time as landscape. We said earlier that clocks tick slower, deeper in gravity, and faster higher up. In general relativity, you can think of gravity as affecting the rate at which time flows. But more precisely, gravity affects the metric, the rule for measuring space-time intervals. That metric tells you how to compute proper time from coordinates. Near Earth, a useful approximation is that the fractional difference in clock rates is related to the difference in gravitational potential divided by the speed of light squared. That is the reason the effect is so small in daily life. The speed of light squared is an enormous number, so ordinary potential differences lead to tiny fractional changes. But tiny is not the same as absent, and with modern clocks, tiny becomes visible. So scientists can move a clock upward by a small height and watch its frequency shift. The clock runs faster, higher up. This is a strange inversion of intuition. You think higher means more exposed, more vulnerable, more thin air, more cold. But in time rate, higher means faster. Higher means slightly more future per day. And lower means slower. Lower means the universe charges you a little less time for your existence in the same coordinate day. There is a very old phrase, time flies. Gravity is the part that decides how much. Now, you might wonder if this means time is a fluid, flowing at different speeds like a river. That metaphor is tempting, but it can mislead you. In relativity, time is part of a geometry. It is not a substance moving through space. It is a dimension with a metric that can vary with gravitational fields. But if you need a metaphor for sleepy understanding, you can keep the landscape one. It is closer to the math than the river one. In a landscape, different paths have different lengths. In curved terrain, straight lines depend on the terrain. In valleys, distances behave differently than on flat plains. Time, in general relativity, is like that. The terrain is space-time. Mass energy shapes it. Clocks are odometers for proper time along paths. That is the story. Now there is a final subtlety that can either soothe you or annoy you, depending on your personality. When we say time runs slower in gravity, we are comparing to some reference far away. But in a strong gravitational field, far away is not always well defined in a global sense. In complex spacetimes, you cannot always pick one universal time coordinate that covers everything nicely. You can do it locally and for specific symmetries, but globally, it can get messy. The good news is, you do not live near a rotating black hole. The bad news is, the universe still does not care. For Earth and satellites, we can define coordinate times that work well enough, and engineers do it. For astrophysical objects, physicists choose coordinate systems that make calculations manageable. So again, now and time coordinates are choices. Proper time along a world line is what a clock measures, and that is the physically experienced quantity. Now, with all of this, we are sitting on the edge of the final sections, the ones where we bring it back to the room and treat time dilation as a quiet feature, not a problem. But there is still more to say before any wrap-up, because there is one last common misunderstanding that is worth dissolving gently. People hear time dilation and assume there is a master clock somewhere, and moving clocks are slowed relative to it. That is not the relativity story. There is no master clock. There is no universal rest frame in the laws. There are frames that are convenient, like the rest frame of the cosmic microwave background, where the universe looks most isotropic, most uniform. You can define motion relative to that, and it is useful in cosmology. But it is not a preferred frame built into the laws the way ether theories once tried to imagine. Relativity says the laws work in all inertial frames. The universe does not stamp one as correct. So, time dilation is not about how close you are to the real time. It is about how your path compares to another path when you meet again. And that is a calmer truth, because it stops the mental struggle to find the correct now. There is no correct now for the whole universe. There is your local now and your causal connections and your meetings. Now, here is one more way to keep it grounded. Every measurement you make involves signals, light signals, radio signals. Through wires, they all have finite speeds. So the universe already forces you to live with delay and locality. Relativity simply builds that locality into the structure of time itself. It says you cannot define distant time without a convention, and your convention depends on motion. So your instincts are not wrong. They are just scaled for slow speeds and small distances where conventions agree well enough. And in daily life, those conventions do agree. Your wall clock and your phone and your oven and your tired brain all form a working coalition. They do not need relativistic corrections to tell you it is late. But when you push precision or distance or speed, the underlying structure shows through. Now, keep that in mind as we continue, because the next natural thing to do is to stop treating time dilation as an exotic effect and start treating it like weather. Not dramatic, just part of the environment. You are always moving through a gravitational field. You are always moving relative to something. So you are always accumulating proper time at a rate that is subtly dependent on context. This means the question, how fast is time passing, is incomplete unless you also ask, compared to what and measured how? And if you want one simple, sleepy takeaway to carry into the next part, it is this: seconds do not misbehave. Seconds obey their local rules. When you move, you do not break time. You take a different route through it. When you climb, you do not escape time. You step onto a slightly different slope. And when you try to demand that the whole universe share your now, you are asking for a convenience the universe never promised. So we can keep going from there, letting the idea of many no's settle in as a normal feature, and letting the body remain the anchor, your local